Thank you very much. I'm speaking about Digtool, a visualization-based framework for detecting kernel vulnerabilities. I'm Xiaocao from IceSword lab of 360 Internet Security Center. The speech includes 6 parts: our contributions, related work, the architecture of Digtool, its implementation, and the method of detecting vulnerabilities, Digtool's advantages, and the future work. The main contributions are as follows. We propose Digtool, that is the backchecking framework. It's based on virtualization technology. There is no compile time requirement. Currently, it's mainly used for detecting vulnerabilities in Windows kernel and detecting device drivers. As a framework, it can be used to detect various types of vulnerabilities such as unprobe, Digtool, UF, OOB, and some other types of vulnerabilities. At present, via Digtool, we have found 45 kernel-level zero-day vulnerabilities of unprobe, Digtool, UF, and OOB in Windows kernel and some third-party driver programs. The main related work was 3 aspects. In fact, Digtool belongs to the first kind of method, the virtualization in emulator-based methods. In this area, the notable tools are Jianfeng and Boxpong. Jianfeng is used for discovering vulnerabilities in parallel visualization device of Zen. Boxpong is based on Box emulator. It has discovered many Digtool vulnerabilities in Windows kernel, but its application is restricted by the performance of Box emulator, and it cannot cover all of the Windows kernel models since the Box emulator is not able to simulate a certain hardware-specific operation of a real-world machine. Another class of tools is dedicated to detecting kernel programs such as driver verifier, memory check, memory leak, and KDR. But only the driver verifier is used for Windows OS, and is not a dedicated tool for detecting secure vulnerabilities. There are also some other kinds of tools, such as source instrumentation based on address identifier, binary instrumentation based variant and duct memory, and the red zone based dieharder. However, most of the tools are used for user mode programs. For these reasons, we propose Digtool for discover kernel vulnerabilities in Windows OS. It's based on virtualization technologies. At first, we will discuss the architecture of the Digtool. Its components are distributed across user space, kernel space, and the hypervisor. Digtool does not rely on any current virtualization framework. We implemented our own hypervisor. In the guest kernel, we install a middleware of communication between the hypervisor and the components in the user space. The rest of components are left in user space. These components are responsible for fuzzing and post-analyze. The hypervisor consists of 3 logical modules. Among them, VMware infrastructure is used for initialized hypervisor and provide basic facilities. Interface detection is responsible for detect unprobe and Digtool, and memory detection is used for discovering UF and OOB. The middleware connects the hypervisor and the user mode programs. For interface detection, it records behavior events into log files for post-analysis. It can help to limit the scope of system calls. Thus, we can focus on safe calls that are interested. The middleware can also help set some switches or configuration file information. For memory detection, the middleware calls calibrate monitored memory Monitor memory keeps change with the memory allocation and release. So it's used to trace the monitored memory. It's also used to limit the monitoring memory area in kernel code. At last, it can interrupt the guest OS at the moment of triggering a vulnerability and provide the context for analyzing the vulnerability. There are three modules in the user space: loader, fuzzer, and log analyzer. The loader loads the target process to provide a precise environment for detecting vulnerabilities. In addition, the loader also distills information from config file to the middleware. The information includes the tested system calls, the virtual address of the boundary for proper access event, and so on. I will talk the proper access event later. The fuzzer is responsible for testing the system calls in a configuration file. It's for code branch by adjusting the corresponding parameters. The last component is the log analyzer. It's used for post-analyzing the potential vulnerabilities to log files. Next, we will discuss the implementation of detailed Digtool and how to detect kernel vulnerabilities. But first, let's talk about VM infrastructure. The main task of VMware infrastructure include two aspects: initialize the hypervisor and provide basic facilities. In the beginning, Digtool is loaded to OS kernel space as a driver. The driver starts the hypervisor for every processor. Then it sets the state of guest OS according to the state of original OS. Thus, the original OS becomes the guest OS running in the VM. There are 5 components provide the VM infrastructure. Among the last 2 modules are associated with the particular type of vulnerabilities. So we'll discuss these 2 parts later. Next, I will mainly describe the first 3 components. The first component is the virtual page monitor. We use the shadow page table to monitor virtual memory address. The workflow for virtual page monitor is shown in this figure. Adopt a sparse bitmap to trace virtual page in process space. Each bit in the bitmap represents the virtual page. If a bit is set 1, the corresponding page is monitored, and the P flag in its page table entry of the shadow page table should be clear. Any access to the monitored virtual page will trigger a page fault exception that will be captured by the hypervisor. So when a page fault exception is captured, the page fault handler in the hypervisor will search the bitmap. If a bitmap of a page that caused the page fault exception is 0, we say not match, and the page is not monitored, and the SPT will be updated through GPT, and such the instruction that caused the exception will re-execute successfully. If the bit is to 1 and is the monitored page, then the handler model will be used to deal with this exception. It will record the exception or inject a private interruption into the guest OS. The recording process for the exception will be described later. Now we will focus on the injected private interruption. The private interruption handler connects to a debug tool by triggering another exception, such as a software interruption in the guest OS. After that, Digtool sets monitor triple flag or triple flag. That is, starts the single-step lab in the guest OS. Meanwhile, the SPT is updated with the GPT. Then the instruction that caused the exception will re-execute successfully. Because of MTF or TF, the VM exit will be triggered after executing one instruction in the guest OS. And then the handler of MTF or TF in the hypervisor has a chance to clear the P flag. And the page will be monitored once again. Finally, it's disable the MTF or TF to cancel a single stepping operator. To achieve better performance with more effective data, we adopt thread scheduling monitor to focus on monitored threads. That is, we only employ SPDs for the target threads that use the original GPTs for non-monitored thread. So the virtual page monitor will not affect the performance of non-monitored threads. The thread scheduling monitor mainly includes 2 points: identifying related data structure and monitoring the data structure. The running thread of the current processor will be obtained through the following relationship. Any vital operation in the current thread variable means a new thread will become to a running state. At last, we will discuss the communication mechanism of Digtool. It contains 2 aspects: kernel to hypervisor and hypervisor to the kernel. Kernel to hypervisor is mainly implemented through a set of service interfaces. This service interface invokes VM call instruction that treat the VM exit. Thus, the service routines in hypervisor can handle the request. Hypervisor to kernel is mainly implemented while shared memory. At first, when a target model triggers a monitored event, a VM exit will be captured by the hypervisor. Second, the hypervisor records the event information into shared memory. If the shared memory is full, it will inject a piece of code to the guest OS. The code will notify the work thread to read the data in the shared memory and write them into log files. If the shared memory is not full, it will jump back to the target model. Third, after notifying the work thread, the injected code will return to the target model and execute the following instructions. Next, I will introduce the interface detection, how to use it to detect, unprobe, and talk to vulnerabilities. We define event monitoring to intercept 10 types of events for identifying vulnerabilities. The first 3 events indicate an entry point of a system call. The write user event indicates the exit point of a system call. Therefore, this event can help to identify the execution process of a system call. The memory access event indicates the user mode memory is accessed by the kernel programs. The purple read, purple write, and the purple access events suggest the user mode access is unchecked. The last 2 events are used to reduce false positives. They indicate the user mode memory is allocated or deliberately accessed by the kernel code, and it has less of chance of causing vulnerabilities. Most of the events can be intercepted by hooking the corresponding kernel functions through intercepting the entries and the interrupt disrupt or MSR registers or via virtual page monitor. But we need some other method to trace the proper access event. In fact, we propose a CPU emulator to trace proper access event. In Windows kernel, program could adopt direct comparison to check the user model access. We define proper access event to handle this case. The 2 pieces of instruction on top of the typical example of deploy comparison. They compare the user model access with the value in user proper access. This value is the user model address space boundary. We call this address of this variable's target memory. And we use debug register to monitor target memory. When the guest OS accesses the target memory, the debug exception handler in the hypervisor will capture it. The handler updates the virtual CPU of the CPU emulator, so the guest CPU of the virtual machine. Thus, the CPU emulator is active to interrupt and execute the code of the guest OS. The CPU emulator forks the CMP instruction and will discuss the user model address, thus we can know which user model address has already been checked. With the basic concept of knowledge, now let's see how to detect unprobable vulnerabilities. An unprobable vulnerability means a user pointer has not been checked before used by kernel code. Or if the kernel code accesses the user memory deliberately, there should be a alloc virtual memory or get PBTV event before a memory access event. Therefore, if we find a memory access event and there is no corresponding event to indicate the user model address is legal, there may be a potential unprobable vulnerability. It is often the case in a complex structure containing user pointers. So the data highlighted in green is the vulnerability is in a vast antivirus software. It fetches the value from the user address without checking, while the subsequent checking instruction belongs to the anti-alloc virtual memory function of a kernel. So it is a typical unprobable vulnerability. Digtool is short for time of check to time of use. In general, it is safe to fetch an input value from user memory only once. Otherwise, there will be 2 or more consistent memory access events that will trigger the same user memory address, and there may be a Digtool vulnerability. So this is the event in Dr. Web antivirus software. The user address highlighted was accessed by the kernel instruction more than once. So a reserve analysis, we can know that at the first time the Dr. Web driver program fetched the value from the user address to check it. And the second time, the driver fetched the value again to use it. Therefore, it's the typical Digtool vulnerability. The last point is memory detection. We will discuss how to use it to detect UF and OOB vulnerabilities. We use memory detection to detect the illegal use of kernel memory. The main idea is to trace to memory allocation, release, and access. Memory allocation and release are traced by hooking the corresponding kernel functions. But we should only hook the underlying memory functions rather than the wrapper function. This can avoid repetitive records. In order to achieve a comprehensive result, besides the memory pool, we should also focus on look-aside list. We focus on 2 aspects of memory use, UF and OOB. UF is short for use up free. We will focus on freed memory. Any instruction operating the free memory is regarded as in the use instruction. The free instruction is recorded when the free function is invoked. In order to get a better detection result, Digtool delays the release of the freed memory to extend the detection time window. The instruction highlighted in green is the vulnerability in Win32 key. The single-step exception is triggered by Digtool. As there is a trip event, the use instruction that calls the UF is just before this address. OOB is short for out of bounds. In this case, We focused on unlocked memory, which is monitored by the virtual page monitor. As the unlocked memory areas keeps changing with memory allocation and release, we need to adjust the unlocked memory area dynamically. Any access to the unlocked memory areas regards the OOB vulnerability. In addition, we also introduced the extra block when a memory is allocated, so the allocated memory areas are separated by the extra blocks, which can help to increase the chance to detect OOB vulnerability. The disassembly code highlighted in green is a vulnerability in Win32K. Just like case in detecting UEF vulnerability, the instruction just before the surprise is the exit instruction that causes the OOB vulnerability. Our Digtool has some advantages. First is crash resilient. It is very effective in detecting some types of vulnerabilities, such as information leakage. In general, it is hard to trigger crash in detecting information leakage vulnerabilities. Second, Digtool can provide an extra context for the vulnerabilities we discussed before. Third, Digtool can discover various types of vulnerabilities and it has some advantages in detecting them. For example, it can detect the UEF vulnerability while it's delayed release, but it's harder for the driver verifier to detect vulnerabilities. At last, Digtool has the better performance. It only affects performance of a tested system calls. In a monitored thread, it has much faster than a box emulator. Finally, I will discuss some possible future work. The first one is performance optimization. There is still so much room for reduced performance overhead in a monitored thread. The performance cost mainly comes from the frequent switch between the hypervisor and the guest OS. How to reduce the switches and the performance cost will be research topic. Second, we can extend the detection algorithm to discover more types of vulnerabilities such as double free, information leakage, and rest conditions. Currently, we are working on detecting information leakage vulnerabilities in Windows kernel, and we have found dozens of vulnerabilities. At last, we can port the Digtool to other platforms. The hypervisor runs outside of guest OS, so it tends to be more portable. The main work of supporting various platforms is adapting the middleware, which is platform specific. So that's all. Thank you.
So we have some time for questions. If you have some, please step up to the microphone, state your name and affiliation, and fire away. Maybe to get this started, let me ask one. So in your last session, in your last slide on future work, you said that you wanted to port, or you might want to look into applying this technique to other operating systems. How operating system agnostic are the detections that you built in your system? Like, do you expect that to be very easy and it just you bring the operating system up and it runs, or do you actually have to change your detection mechanisms?
Yeah, our hypervisor is run outside from guest OS, so it's placed from independent. We just only implementation middleware part is all of the work on the middle part, not on the hypervisor. So it's easy to port to other platforms.
Hello, I'm Jianfeng from Chinese Academy of Sciences, and I have a question. you introduced clearly about how to detect vulnerability, and before that you must fuzz the kernel. So can you talk more about how to do the fuzzing to trigger the vulnerability?
You just mean code coverage?
Did you do some extra techniques to improve like code coverage or other things?
Yeah, we use inter-PT. Do you know inter-PT trace?
Yeah,
yes. Yeah. We use this for increase our code coverage. We use the fuzzer, but it's not the only focus point of this talk. We will talk about this topic later. We use, if you have any question, you can send an email to us or have a face talk.
Okay, thank you.
Maybe while you're still thinking of more questions, let me squeeze one more in. So you decided to implement your system based on your own hypervisor. Was there a specific reason that you wanted to avoid, let's say, Zen or KVM or any of the off-the-shelf hypervisors that are already out there?
Sorry, we asked again. I'm not.
As far as I understood from your presentation, you implemented your own hypervisor for Digtool.
Yeah.
What, is there a specific reason that you could not use KVM or Zen for that matter?
No, we don't use any current hypervisor framework. We implemented our own hypervisor. It is a new hypervisor framework.
The reason we didn't use other hypervisor, just we have researcher is working on how to create something new, so that's just simply we create one from by ourselves.
All right, I guess it's fair to switch over to the next presenter, unless there is someone at the microphone. No, there is now.
So
let's thank the speaker.
Yeah. So if you have any